Welcome back from lunch, everybody. If I can keep you awake for a little while longer, I'll try to, so the next person can get up here and actually teach you something. And I'll apologize up front ahead of time if I sound like a Holstein cow waiting on the milk barn door to open up. I've had some serious sinus problems since I got here this week, but I want to do my best to get this out without blowing and snotting and carrying on, so just pardon me, my southern slang will just fall out if that happens. But we're going to talk about alternative power sources for your access points. A lot of times we have remote locations that we need to put APs out. And if you've ever done that before, we find out that the power source is really the worst problem that we have finding. A lot of times, you can't really run Cat 5, 700 or 800 feet out and run a POE or injector like that. You're not supposed to. I know some people still do. But what I'm going to do today is give us a little bit of a rundown on the mathematical calculations on how to create your own power supplies. And I've been doing this for about 5 years with a government customer. And of course, one of my designs, our sponsor back here, Ventev, has actually been building one of my designs and supplying it for me. So I'm going to go ahead and get started. And here, this is a slide that's a little bit about me. I really don't not singing my own accolades here, just wanted you to look at the bottom one for people like Blake that take pictures of me playing a piano and putting it on, just... No, I just recently got my master's degree in the World Taekwondo Federation, and that's been a lifelong achievement. It's been about 30 years working on that. I've been on the slow bus because of my love for Wi-Fi. But do want to show you some stuff that I'm using, a business that I started a couple years ago. We power 75% of our business. It's a kayak and canoe rental place in Winchester, Tennessee, and we power 75% of the power that we use is solar. And so you can see over there that our boat rental check-in, check-out stand is powered by solar. You can see the middle picture there, how they're wired up. And the little small Neem enclosure that's got the solar controller and the battery on the back of it to advertise and light up our paddle boards. And here's our lake map with just basic solar things. So solar has become something that's really relevant in the world today. And so what I'm going to show you is an industry version of it. And of course, because it's a government location, I could tell you where it's at, but I'd have to kill you. I don't really want to use my black belt today. So no pictures, Blake. All right. Right here in the middle picture, so you can see inside the cabinet, we got our batteries and our solar panels and things like that. We've got our access point up, providing outdoor Wi-Fi location services and things like that at high industrial locations that have been working flawlessly for 4 and 5 years. This particular type of technology works great for Wi-Fi, and it's been a very great alternative for me. And I guess some of you may know this if you've worked in power companies. If you are trying to use power from a power company, you know that it sucks. They have very undependable power, so you have to come up with your own power if you want your network to stay up. So this is what I did. I actually designed this particular system, needed somebody to build it. Ventev had the technology and the people to build it for me, and I've been using them to use this for a long time. But as we move on, we're going to use this as a project today. So we're going to start a project so that you can learn how to do this. Those of you that have electronics experience, you know what we're going to go through, and it's basically calculating power, current, voltage, things like that. But we start out as a project, and our project is we're going to power a remote AP, and we're going to provide Wi-Fi out to this remote location when we power this remote AP. We're going to meet the stakeholder requirements, so we're going to talk about what the stakeholder requires, and then the device we're using today is going to be the Cisco 1552E. I picked this one because it's a big beast. It uses a lot of power. It uses non-standard UPoE, so it uses more power than what you would usually use on something that's PoE, PoE plus, something like that. So we're not talking our usual 15 watts or 30 watts. So what is the project requirements? So we're going to talk about those. We're going to need 60 watts of continuous power for this access point. We're going to utilize the 12-volt DC power input instead of the UPoE 56-volt input. We want system failure redundancy, which is 7 days uptime. So explaining our 7 days uptime, if we happen to lose the charging source, in this case our charging source is going to be our solar panels or our batteries or a combination of one of the two, the AP will function for 7 days without a charge assist in any form or fashion. And that provides 7 days to find and repair the issue. If you're dealing with government, you know they're not going to get right out on a ticket that day. They're going to throw it on the table and wait. So that gives you 7 days to actually find out that there's something wrong. Sometimes you don't even know there's something wrong because someone doesn't report it that quick. So the other thing we want to do is make sure with this 7-day window that we don't have a complete discharge of our batteries, because batteries, once they discharge past 80%, you damage them and they're not going to be efficient anymore. So the 7 days uptime is to protect equipment, give you plenty of time to protect the network to keep it from going down. So Ohm's law, power is current times voltage. We're going to go over that. Some of the things that we need to do, we have our power. Our power is 60 watts. We need to provide 60 watts. And we have our voltage, a 12-volt DC power input. So we want to solve for current. We divide our 60 watts by our 12 volts, and we get 5 amps. So our system today on our project, we're going to have to come up with 5 amps continuously around the clock for that 7-day uptime to make sure that our access point don't go down. So how are we going to do that? Solving for our uptime, we're going to measure that in amp hours. That's 5 amps being consumed every hour on the hour. So you go 10 hours, you need 50 amps. 24 hours times 7 days is 168 hours, and so we have 168 hours times our 5 amps. We need to provide 840 amp hours for this project in order for this project to work like we've been directed by our stakeholders. And solving for our 840 amp hours, we have 168 hours times 5 amps gives us that 848 amp hours. And for the sake of this project, I'm going to use the deep cycle 6-volt DC batteries. Now we could use the 12 volts, but there's another piece of electronics technology that I'd like to teach, so I'm going to use the 6-volt battery in order to teach this so that we can all understand series and parallel batteries and circuits. So the 6-volt DC battery we're going to use is a 200 amp battery. It's a deep cycle battery, which means it has a 20-hour rating and not a 10-hour rating like maybe your car battery would have or something like that. What that means is for 20 hours straight, this battery can give you a consistent 10 amps of energy to a load for that solid 20 hours and not deviate from that. When you go over 20 hours, and this is important, when you go over 20 hours, you start losing that factor of stability, and your consistency goes down because now you're starting to damage the battery. So batteries in series, we're going to look at this. If you take our two 6-volt batteries and you connect them in series together and then use the red wire off of one and the black wire off of the other one for your load, you've now got 12 volts, but you didn't do anything with your amp hours. You still have 200 amp hours and 12 volts instead of 6. But when we look at this, this is not what we need, right? We've got to come up with higher amp hours. Remember, we had to have 840 amp hours for our circuit. So here's how we do that. We take this same 12-volt circuit that we did in series and start stacking them in parallel. And now we're not adding our voltage, we're adding our current. So we've taken a 200 amp hour circuit and a second 200 amp hour circuit and added them together, and now we've got a 12-volt circuit with 400 amp hours. But that's not what we're looking for. You remember, we need 840 amp hours, so this is the circuit we need to build. We need 10 of these batteries done in 2 battery series, run in parallel in 5 stacks together. And if you'll notice, we've got 1,000 amp hours. We only need 840. But remember, we're going to run for 7 days straight. We're going over that 20-hour mark. So I've built in a contingency window of 160 amp hours to help us with the deviating from the consistency of a 20-hour discharge. We'll start going over those discharge rates here in a few minutes. This is the device that we're actually going to replace. Those of you that's worked with any Cisco equipment in the past, this is a beast of a power supply. It will do regular PoE for your 15 amp or 15 watt devices, and it'll do all the way up to 80 watts peak, 60 watts continuous. But it runs 56 volts DC, max current is 1.43 amps. And when you multiply that out, you can see that you got 80 watts peak power that will come out of this. So it will surge up to 80 watts. Now, the next thing we're going to go over here, if you look at these category cables that I'm bringing up, these category cables, when you're supplying power to your access points, all of these that I've listed here will supply that 1.43 amps to an access point. The wire is big enough to carry that kind of current. So what we are looking to do and why this is important, if 56 volts will run the 80 watts, then 12 volts, what kind of current you think you got to have for the 80 watts there? You look what the current does, because the number one thing you're looking for is the wattage. When you're using a switch, you've got a constant, and that constant is the power going to the access point, right? So the 80 watt number here is what we're looking for, a constant. So if we drop our voltage, we got to raise the current number so the basic math stays the same to get the same answer. So at the peak power, we've got to have 6.67 amps. And the UPOE source for the 1552 is 60 watts. That's the continuous power. So if this AP was running at top power, clients on it, keeping it loaded down with all of its antennas, it would burn 60 watts continuously. So again, 56 volts at 1.07 amps is 60 watts. But we drop that to 12 volts and we end up with a whopping 5 amps. Now, drop back to the Cat 5 and Cat 5e, Cat 6, all those smaller cables. It's very important to realize, if you look at these, 24 gauge wire in your Cat 5e will only take a half amp. Your 20 gauge wire in your Cat 6 will take 1.47 amps. Cat 6A does have a special brand that will do 18 gauge that will take the 7 amps. But remember, we've got to have 5 amps of power going up this, so we cannot use Cat 5e and we can't use Cat 6. We can use a specific type of Cat 6A that comes specifically in an 18 gauge wire. And all these are also based on 50 feet rating. So if you're going over 50 feet, you do have to start calculating for resistance in the line. So with our circuit, we've determined now with looking these up, and you can find these numbers on multiple websites that will give you voltages and drops and things like that, and current ratings on types of wire depending on the type of wire you're running. But we're going to have to use 18 gauge wire for our circuit. So we have our battery bank. So we've got our 12 volt 1000 amp hours set up in our circuit with our series and parallel design here, and we have our access point. So we've determined that we're going to use 18 gauge wire. Now, I decided right here at this point, because I have experienced this the hard way, if anybody's ever had to get in a car and drive for 4 hours straight to go teach a certified union electrician Ohm's Law, you will put this in your notes and your memos from now on. You cannot use Cat 5e running 5 amps. It just won't do it. And I had that happen in 2 or 3 states where I had to go tell them to change the gauge of wire. But the AP itself, what happens is the AP powers on with that Cat 5 wire, and it hasn't turned on any radios yet. It's going through its sequence, and all of a sudden the 5 gig backhaul kicks on at full power. And it can't get enough juice up that wire because that 5 amps heats up the wire. Heat causes what? Impedance. Resistance in the wire, there's a voltage drop. Voltage drop hits, the access point itself says, hey, I don't have enough power to do this. I'm going to reboot. I'm going to try this again. So that dude will do that for weeks, months, however long it takes to run the battery dead, trying to reboot and get that AP to turn that radio on because you didn't put the right gauge of wire on it. Everything else can be flawless, but your wire is too small. And I have dealt with this several times with union electricians that I have to teach Ohm's Law to. So if y'all design these, be sure to put it in the memo what gauge wire to use. And based on the amps that you run up, I mean, you could have a 10 amp circuit, but make sure you design and put the right wire in. We could literally go to Home Depot and get some 10 gauge or like some 8 gauge stove wire or something and run it up, wire big enough to be jumper cables for an ambulance or something, and it would still work, but it's got to be 18 gauge or larger. But now our batteries are going to run dead because we've got nothing charging them. So here is our important factor. This is the most important part of the whole deal. We've built our circuit, so we have the power supply built that's going to supply the alternative power. Now we've got to find out how to charge this thing and make sure that it don't run dead. And that's a tricky thing based on where you live, what the weather's like, how much sunlight you've got coming in, and so on. So I'll go ahead and give you a disclaimer right now. If you want your circuit to work, you pick out the shortest day of the year, the nastiest weather of the year, and the AP running at its maximum capacity, and you build your formula off of that, which is what I've done. So my recharge rate is based on the mountains of Tennessee about December 25th, Christmas. So our recharge rate here, we have our discharge rate, obviously, of 5 amp hours. Our AP is going to pull 5 amps every hour on the hour until the apocalypse takes place. So charging for our design it's going to stop around 7 o'clock, 7 p.m., and it's going to start again about 6 a.m. in the morning. So what that means is we've got 11 hours of discharge with absolutely 0% recharge rate. But of course, we've got a 24-hour discharge, 11 hours that are, we've got our other 13 hours throughout the day that it's discharging as well. But we only have 5 hours of peak charging time out of those 13 hours. Now, there's websites out there that you can look that up for your region. You can actually punch in your zip code or your area code and stuff, and it will tell you you've got 4 hours, you've got 3. If you live in the Antarctic or you live in Alaska, you're in bad problems. We're not going to be able to use this technology around the clock year-round, but when the sun's up in Alaska, it's up. So now we're going to look for our recharge formula. Our daily usage, 24 hours times 5 amp hours, we're doing our basic math now, we need 120 amp hours every day out of that battery bank to keep this AP up and running. So our average peak time is 5 hours. What does that mean? 120 amp hours divided by those 5 hours means every hour on the hour during those peak hours, we need to put 24 amps back into our battery bank. That's an important number to remember. So we have our current, 24 amps. We have our voltage, 12 volts DC. How many watts do we got to have? So 24 amp hours, 12 volts DC. Use the Ohm's law, we need 288 watts per hour going back into those batteries and able for this thing to work flawlessly and not discharge your batteries. If you mess this up, if you base it off of, let's say you test your AP, and we'll go back and get off my disclaimer in just a minute. Let's say you test your AP and you say, well, Brett, I know you said this AP pulls 5 amps, but mine's only pulling 2.1 or 1.7. Yeah, that's because it may be setting idle, or you've got it turned down to 15 milliwatts or whatever it's running, and there's no clients doing any traffic, or maybe you're using 2 antennas and not 3. But your worst case scenario for that AP is 5 amps. If you design this thing, the power supply, for the little bitty factor that you're reading right now, and then later on you decide I've got to turn the power up, add more antennas, and the more clients are getting on it, so the AP is working more, it's going to consume more energy, and now your power supply is flawed. So you want to design it off your worst case scenario. So that brings us to what size solar panels do we need? Now, solar panels, they come in all forms, shapes, and sizes. You can get them in 6 volt, 12 volt, 24, 36. You can get them in 10 watts, 100 watts, 200 watts, depending on how much money you want to spend, how big they are, who's got them on sale at Kmart or what have you. Tractor Supply and Home Depot, all kinds of different places sell. Harbor Freight is a good one. They sell all kinds of, solar panels that comes with charge controllers and everything. You can get different deals based on sales all the time. So when it comes time to calculate this thing, based on your circuits, you can actually use all kinds of different solar panels if you know how to calculate the formula. So with ours, we need 24 amp hours every hour, 288 watts per hour. So we're going to pick the 70 watt solar panel. So 280 watts divided by 70 watts means we need 4 in a very small fraction, so we're going to go with 4 solar panels. So that gives us 280, and that's 8 watts short. Now later on I'm going to calculate and show you where that really doesn't mean a lot to us. But 70 watts divided by 12 volts DC means that we're getting 5.8 amp hours out of this circuit, out of one solar panel, and all 4 solar panels are giving us 23. Remember, we needed 24. So we're really close to exactly what we need for those 5 hours. So we're going to go with that. 23 amp hours times our 5 peak hours, we're about 3.5 amp hours shy of the 120 we're looking for. Now, here's where you start looking at your solar panel efficiency. We obviously know if you've got a solar panel out there and you shine a flashlight on a solar panel, there's some sort of energy being calculated and created through that solar panel. So solar panel efficiency, if we look at the 116 and we need 120, is this sufficient? Well, that's during our 5 peak hours that our efficiency is 100%. So we get 23 amp hours in a peak hour, but let's say at 5 a.m. it's performing at 10%. So that 10% we're going to get 2.3 instead of our 23. So we have that, and now let's say at 6 a.m. and 6 p.m. it's performing at 20%. We can calculate that. We're getting 4.67 amps at that particular time of the day. So we got 2 hours giving us 4.5 amps each hour. Now, let's move on up one more hour. I'll jump through these kind of quickly. At 7 a.m. and 5 p.m., performance has jumped up to 45 or 50%. And again, this is during the winter. This is not during the heat of the summer. During the heat of the summer, 5 p.m. is probably still giving us 80%. But I'm working off of late winter numbers where the sun is up the shortest amount of time. So now we're getting 10 amps for 2 hours of the day. And we'll do one more just to show you, and making the point here at 8 a.m. and 4 p.m. performance is 70%. So that gives us 16 amps for 2 hours of the day, giving us another 32, 33 amps of power going into this. So what does all this really mean? All these different times where we're getting all this extra power, remember we only needed like 3.5 to have exactly what we needed. But what this really means is we have a high potential for overcharge when we're working on our 5 peak hours in our worst case scenario. So what we have to do to keep from damaging our batteries is we got to have charge protection of some sort. And that's where your solar controller comes in. You have a charge controller, and what they do is they keep your deep cycle batteries from overcharging, keep you from damaging them. And I've seen the prices on the batteries that we use. I've got batteries that's like this long, that tall, and they weigh about 120 pounds a piece. And the price tag is enormous. But they've been running for 5 years now, flawlessly, and it's been worth the money. What you don't want to do is have too much power going into them on a continuous time and just blow the dielectric on your platelets and ruin the batteries and lose your investment. The other thing it does is ensures the power does not run backwards to your panels. And if you know anything about batteries, if anybody's ever pulled their farm truck up next to a tractor or anything else that's got a dead battery, and me living out in the country, I've done this every day most of my life. You got a vehicle with a fully charged battery, and then you got a vehicle with a dead battery. The electrons in the full battery, when they get connected to the other battery, all they want to do is balance out. They don't know they're charging this battery. They don't know that they're discharging. The only thing they know is we got to balance out so that the pull is no longer there anymore. Equal amount of charge on both batteries means that there's stability in the two batteries, and it thinks it's in a circuit. When you discharge your 10 batteries, you don't discharge one battery or one plate, one bank, and then go to the next one. All 10 discharge together. You may pull off the one up closest, but you discharge off the one up to the top, and the others are discharging into it, balancing off on a regular basis. So if you hook a solar panel up to a battery, when the sun's up and lights on it, it's providing power that's more power than what's in the battery. It will be charging. But just as soon as you have your 13.4 volts in your 12-volt battery and the sun goes down, this battery thinks, I'm connected to a dead cell, I need to charge it. And that battery will be discharged and dead and damaged before daylight. because it'll never charge up the solar panel, but the solar panel will drain the battery. So you need to make sure that you have a solar charger. You can't just go directly to the battery to charge it. Now, they come in two different types, PWM and MPPT, and I'm going to quickly go through those. The type differences, they make some pretty important differences. If you're going to vary on your solar panels, there's one that you need if you're going to have direct, like you've got a 12-volt circuit and a 12-volt solar panel. This pulse width modulation is the one you need. During bulk charging, the array will actually, once it gets the batteries charged completely up, it will downshift and sense the load that's being pulled off the batteries and only supply the 5 amps to keep the load charged so that it's not draining batteries. The one thing that it does not do is you cannot add like a 24-volt or 36-volt solar panel to a 12-volt circuit and use the PWM charger. It won't work that way. You also have set points, and this is important. The charge controllers on both of them will protect your batteries from being discharged. Remember I said the 80%, once they get discharged so low, you'll start damaging your batteries. Both of these will recognize that the load is getting below a threshold point that you set, and it will take your load, it will shut your AP down so that the AP doesn't discharge the battery too much and damage your battery. And then once the solar panel charges back up to like a reconnect voltage of 12.5, it'll open the circuit or close the circuit back and allow the access point to charge back up and kick back on and start working again. This is a protection mechanism for your batteries. So that's called your low voltage disconnect, and I just went through this slide here about the discharge, and there's a website that has a lot more about those particular charge controllers on it. And there are a whole lot of charge controllers out there that you can use that will do the job based on what you're looking for. If you're looking for something really elaborate, you want to go to the next one we're going to talk about. The maximum power point tracking charger, it measures the voltage of the panels and then down converts it. So you can basically use any voltage power supply, any voltage solar panels that you want to use to charge your 6-volt or 12-volt batteries, because this charge controller senses the voltage, downshifts it, and uses it for your 12-volt circuit. And one of the things that it does, it actually helps raise the current, and it has a sensing module in it to sense that the batteries are really low, and it can step up the current to charge the batteries quicker while actually providing more current for the device that's connected to it as well. So you can kind of change your formula a little bit to save money on your battery bank. All right, so we went over this just a second ago. The big difference between the two is this right here. The battery bank itself can be any size solar panels with the MPPT. But with the PWM controller, if you've got a 12-volt circuit, you have to use 12-volt solar panels. So with those in mind and all this stuff that we just read over, how do we find out which controller we want to use? Because there are so many different types out there. There's actually one that's got this neat little gadget where you can pull out your phone and walk up to it and connect to that thing and pick it up from at home and see how much power it's doing. You can look at the history of it and see how it's produced power and what its performance has been for the last 24 hours and all kinds of neat stuff. So how do we decide which one that we need? Well, the biggest difference that we will look at again here is the PWM solar array, and here is a picture of the Harbor Freight. This costs you about $150 at Harbor Freight. You get a 100-watt solar panel kit with all the wiring and the controller and lights for $150 to start playing around. The only thing you don't have here is your access point and your battery. You have to buy your battery second. But with the MPPT kit, your solar array doesn't need to match, so here's a good option that you have to where you can vary on your solar panels based on what you may already have or what's on sale, or the size makes a big difference. If anybody's ever put something up out on a light pole, you know you have to do some wind surface calculations to find out what the pull is going to be from the wind. So that size is going to make a lot of difference on how much solar panel you want to put out on the pole. So you may come up with a smaller solar panel or 6 small ones to come up with the same thing as one big one, but you've got less windage on it. So that can factor in based on your calculations of your pole. So MPP charge controllers defect and modify the charge, and that helps us a lot because it benefits to charge our batteries quicker and ultimately recharge due to a bigger array of, just like we talked when we started out, if you've got 56 volts running a small current to get the same wattage, this thing can drop the voltage on the controller and up the current so that you can speed up the charge process until it gets its charge, and then it can step it down to be able to trickle charge just like the PWM did. So how do we select our charger? It's ultimately based on the total watts of your solar array and the voltage of your system. So like you're looking for a breaker at your house. If you're going to run a 50 amp welder, you need that 50 amp breaker. If you're running your refrigerator or a stove or something like that, you pick out a dedicated breaker. Our solar controller chargers are about the same way. So our system has got 280 watts at 12 volts, so we're going to be running 23 amps in it continuously. So we need at least a 30 amp charge controller. So that's how we pick out our charge controller size, because it's rated for 30 amps. So with all this in mind, we got our project materials list. So we're going to need 4 70-watt panels. We're going to need 1 30 amp MPPT solar charge controller, 10 of our 6-volt DC 200 milliamp batteries, or 200 amp hour batteries, excuse me, and 50 feet of 18 gauge wire, and 1 weather resistant NEMA enclosure to put our circuit in and build it all up. And that entails what we have now is we have the complete power source to hang our AP out wherever we want to put it and turn it up and run it. And we have the solar capacity to keep it running at worst case scenario. And we have a 7-day window, so if a great big Tyrannosaurus Rex steps in front of the sun and blocks it for 7 days, your AP is still up and running. So we have a good contingency plan backup there for that. So what we've calculated here today will give us the worst case scenario for our power system for solar, so that even during the summertime, it's going to run flawlessly. During the wintertime, you know you have your contingency plan. So with all that in mind, anybody got any questions about it? I put everybody to sleep, or, yeah.
Hello? Yeah, if in the summer your panels are making more power because you scaled this for the winter, and that charge controller doesn't send it on, where's all that power go?
Well, the solar panels have the capability of making more power longer, but the solar charger will only take in the amount that it needs. Once it's kind of like just flipping a switch and turning the power off, or it scales it down. That's what the charge controller does. If the solar panels are up, and let's say you've got 7 hours of peak sunlight during the summer and only 4 or 5 during the winter, it's going to charge it a whole lot quicker. And in the first 5 hours of that peak time, it's going to be charged. And the last 2 hours, it's still going to be dropped to a trickle to just carry the load. So you're not actually going to get the benefit of the extra sunlight.
It's still going into the panels. The panels are still making electricity. They're still flowing down to the charge controller. Does it get turned into heat, or does it get dumped someplace?
Well, it actually doesn't. It can provide the electricity. So it's like when you've got a wire plugged into the wall, as long as the switch is turned off of that wire, there's electricity on the end of that wire, but you're still not having any benefit of it because the charge controller's turning it off because it don't need it. So anytime that your charge gets to a point to where you're efficient, it's going to turn down and use only the power it needs to run the load while the sun is up, and then it's going to block the batteries from backfeeding when the sun sets down and just run off the batteries. And just as soon as the sun comes back up, it's going to sense a good enough current to start charging the batteries again, and it's going to turn it back on as it needs it. That's what the wisdom of the charge controller does. So you've still got all that sunlight that you can harness, but it's just like you don't have a solar panel up there harnessing it to put it in anything because you don't need it. Does that help answer the question?
Hello? It was still being made. Unlike power on the walls, there's some company that's taking up and down hydroelectric power to adjust. Right. Those solar panels are still making electricity. It's still coming down to the input side of the charge controller. When it stops, where do the electrons go? It
just stops it. The current has got to have a flow from negative to positive to be able to flow and go somewhere. If you cut that circuit off, it stops at the end of that black wire and it won't go anywhere until you connect it back to the red one.
Thank you.
Got one over here.
Here we go.
Cheers, thanks. On your recharging circuit, you're using a 10-gauge wire to take the 23 amps to the batteries. I'm sure you got to have fairly heavy cables coming back in from the controller to the batteries to recharge.
Oh yes, when you when you buy your battery kits and everything, of course when you buy your battery kits, they actually come with I think it's maybe even a 4-gauge. It's a very big wire, but it's a very big wire that comes off your solar panels into it. But you do have to calculate for that as well. So for the sake of the time that I had here, I couldn't get into every single wire I had, but you will have to do that same calculation from your solar panel. So you're running 23 amps out of the solar panels, and you're running all that to your batteries as well. And so your batteries have got 1,000 amp hours. So you've got to be able to handle all that discharge out of the batteries. So the same calculation has to be done for the panels and the battery bank as well. That's a good point. Thank you for bringing that up. Anybody else? You got one back in the back here. No, I wasn't singing directly to Tom. That was just a flaw. That didn't happen.
Hey, Brett, real quick, what's cheaper, the AP or the tin batteries that you have to buy to keep it running?
What's cheaper, what?
What's cheaper, the AP or the tin batteries that you have to keep it running?
That would depend on which batteries you get. Now, the batteries that I get from Ventev, yeah, the AP is cheaper. But remember, the ones that I'm using are powering for a government resource, and they don't want the apocalypse itself to make that AP go down. So, I have to get some very hefty batteries. But now you can I've even run these things with trolling motor batteries for a boat. I've used them before. They're good deep cycle batteries. So, all right, we got time for one more question.
Follow up. That's per AP, correct? So if you had 5 or 6 APs, you would need 5 or 6 of those type solutions, correct?
Right, that is correct. So you're going to build this same solution for every AP you're going to put out in a remote.
Did you isolate these or do anything for lightning suppression?
Isolate them for lightning, yes. They are grounded and got I think it's 6-gauge green wire that goes straight into a lightning rod and things like that on them. But yeah, they all have to be isolated because most of the time you're going to put them on a light pole or something like that out in the weather. But if anybody would like to talk more on that, I think my website is, or my blog is available, my email is available, my cell phone. You guys just get in touch with me if you want some more information. And again, Ventev, if you come up with a solution that you need, they've actually built this very complicated system that I designed to satisfy my government customers. So I'm pretty sure they could help you out and design that thing as well. So outside of that, the only thing left to do after you get your system and get all your system built and designed and you got your AP on the pole and put all that stuff in is you just turn up your radio. I appreciate it, guys.